discussing the events 4.8 to 4.12 part 4, two presentations. One is Jiajun Wu from Stanford. He's talking about seeing physics, basically the inverse problem of computer graphics, how to turn 2D into 3D, how to replicate images in capturing physics, capturing texture, capturing. He's actually talking about multisensory capturing. So it's not just the vision, it's sound, it's haptics. His PhD thesis is going back to the problem of how to see physics, basically. So can we use computational vision technology to replicate physics, which goes exactly into the realm of what Jitendra Malik spoke about recently, which is if we can solve 2 to 3D, so if we can solve 2-dimension to 3-dimension and physics, if we can see physics, we can simulate from video and images. With that, we can teach robots how to grasp or move around in nature. In sim, we can use reinforcement learning. We can iterate billions of times at hopefully low computation cost, or much lower cost than if we had to do it in real. Then we just solve the sim to real problem, which according to Jitendra is not as big. And then, we have a bootstrapping for robots. So I think Wu is in that realm. I think he's one of those researchers, by the way, you should pay attention to. He's good. Let's just leave it at that. I think I need to make an episode just about that. In my work, I come across a lot of scientists, a lot of researchers, and every now and then there's some really good ones there. Wu also, in one of the other papers that I'm discussing here, talks about foundation models for robots. So generally, he wrote a paper with colleagues about just a summary of what's out there. But fundamentally, a lot of the stuff that Wu is trying to do in his PhD and in later works is sort of task specific, right? You want to capture an image, you want to render it in 3D, you want to capture the texture, you want to capture the dynamics, you basically want to capture the physics. And the question is, can foundation models actually do that? Because in large language models, foundation models have the ability to sort of to acquire tasks. So the more compute you add and the more training you do with mask autoencoders, the more they learn. And the question here is the same. Now, in his paper, he's listing 5 still open research questions in foundation models for robotics. One is data scarcity. One is high variability of robots, sort of the embodiment problem. One is uncertainty quantification, which just means, okay, is this thing going to hallucinate? And if so, when? Safety evaluation, even outside of hallucination, what does it mean to be safe? This goes back to Karen Long's work I discussed in the previous episode. And then real-time performance is a computation memory question. How can we do inference from foundation models? So again, Wu is one of those people one has to pay attention to. He's really good. He's an interesting person, inspiring. The second presentation is by a professor. I'm just going to use his first name, Ashwin. He's at CMU. He's developed an engineering solution to a similar, or let's say it that way. He's solving a 2 to 3D problem through engineering. What he's doing is he's building a lens that has computational abilities to simultaneously focus on different parts of the picture. Now, the way this is done is, in a sense, is using classical optic methods, things like taking light, turning it through a Fourier transform into what's called a Fourier plane. Think of it like you're taking in a picture and then you're transforming it into what's called a phase space. In that space, you can work with it, and then you're creating like a prism. You have different slopes of that phase. You then have this spatial separation in a sense that different parts of the picture can be locally focused, and therefore you have a computational method to locally focus different parts of the picture at the same time. One method this was done before Oswin's work is what's called time multiplexing, which is take an image and think of it like you're taking several shots of the same image, and then you refocus each shot, so that way you have kind of the same effect, which is different parts of the image focus differently. In this case, you take one shot, you do this computational translation, you're using optical techniques which aren't terribly new in a sense, but the combination of those techniques is new. And what's most importantly, it's computationally, you have computational and electronically defined processes. You can then apply this to, for example, render 3D scenes. And as you can maybe sense, this actually is going into the direction of Wu's work, right? Because now we have an opportunity to take 2D pictures and images, turn them into 3D. And if we can have some learnable, translation matrices here and add some physics and texture and maybe, embed it into the foundation model, next thing we know, we have a better translation from 2D into 3D. So this episode is dedicated to the inverse graphics problem, which is how do we get from 2D to 3D? And the goal for us here at Orange Capital Partners, and for generally, I think a lot of the robotics community is working on this, because this is one path towards better simulation. As Wu says in his foundation paper, one of the problems of robotics is data scarcity. We could solve that with simulation. This is the Not Even Wrong podcast. It's April 14th, 2024. This is Krim Delco. It's a Sunday. There's no update. For the year, we are down 19.2%. The market is up 6.8%. We're underperforming by 26%. So the first presentation I want to talk about today is Professor Wu from Stanford. He is in the business of trying to solve the 2D to 3D problem. His PhD thesis is from MIT, where he worked on seeing physics. In other words, finding ways to computationally turn 2D images into 3D images with physics attached to it and dynamics. There's a lot of interesting work here in terms of traditional control theory, translation matrices, Hamiltonians. This is within that realm, but I think Wu's work is a little bit more interesting because he's adding some ideas, in particular the learning part, right? He's trying to embed this problem into a deep neural net type context. So he's trying to parameterize translation matrices from 2D to 3D and find ways to efficiently do that. And the main question is, how much symbols do we need? How much logic and how much just pure data? Where is that sweet spot? He's actually in the abstract of the presentation that he gave, he writes that the key of his work is to find flexible generalizations and representations of images that then can be used for robotics. He's also talking about unsupervised learning. That's important. So this goes into the direction actually of foundation models, right? You want to have maybe an unsupervised way to learn about the physical attributes of objects, and that really brings me to the key inspiration of this talk, which is I think that after I listened to the OpenAI guys, one of the biggest takeaways from the large language model research so far is that we have this sort of sequence of tasks that is learned through training. So a large language model learns how to fill in gaps. It learns grammar. It learns language. It learns translation. It's almost like task specific. And Why that's the case, I don't know. But the point here is that it's conceivable that if we build if we build an image, let's say we build an image net for robots, a massive data scale of video data, images and video in particular. So we capture dynamics, we have the fourth dimension, and we're able to translate from 2D to 3D. We then have the foundation for a massive data set that then can be applied in, let's say, reinforcement learning contexts for robot learning. This is, again, this is the holy grail. This is what we're working towards as a community. This is what we're looking for as investors. And some of the let's say some of the key problems that Wu is tackling is perception. So classic perception is not just vision, it's also, he calls it multisensory. So there's sound, there's just haptic stuff, physical interaction. How can we build dynamic models that quickly adapt to complex stochastic real world scenarios, and how can we contribute that this whole idea to planning and motor control, right? So think of a robot here as a machine that, you know, grasps stuff and cooks and cuts and has a sense for the physics of the objects that it interacts with. This is the key. And I think Wu talks about what this brings up is really the idea, okay, how do foundation models work? Can we have foundation models? And Wu brings in one of the more cited papers recently, he has a summary of foundation models for robotics, 5 points that he points out as open research questions or challenges: data scarcity, how to obtain internet scale data for robotic manipulation. Second, high variability, how to deal with the large diversity in physical environments, physical robot platforms, you know, the embodiment problem. Uncertainty quantification, how to deal with, let's say, hallucination or something along those lines. Distribution level uncertainty. So what that means is you train a robot in a forest and then you put it in a desert. How can it move there? But I think if we can go in sim, we can solve that. Safety evaluation. This is Karen Lung's work. Basically, how do we know a priori whether a robot is safe, and then real-time performance. This is a computational question. So I think to summarize, Wu's work is incredibly interesting. It's just it captures this inverse graphics problem really well. That's his work. That's where he lives. He's trying to solve it bottom up, data only, unsupervised, foundation model, but also top down. Can we add symbolic logic? You know, let's throw in Douglas Hofstadter again. I'm reading the book I'm a Strange Loop, and it just always comes up, right? We humans, we have this ability to abstract, right? But the word soap opera means something to a lot of people in the English-speaking world. And imagine if you had to, like in Hofstadter's book, you had to explain soap opera in Old Sanskrit, right? In a language that was spoken when there were no soap operas. How would you explain that? You would need a lot, this, you know, high Kolmogorov complexity here. And the same applies to I think Wu's work. Okay, we can translate maybe how do we get from pixels to physics? What does physics mean? Physics means the agent has a sense for what it's interacting with, and do we have to do this soap opera old Sanskrit type super complex, difficult, and computationally intensive translation? Or can we have maybe symbols? Can we have something like soap opera in the model so the robot doesn't have to learn what that is? Again, back to the LLM story, it seems like large language models have the ability to do that. And maybe we can combine large language models with vision, which is being done. And I think the addition of semantics to raw pixel analysis and potentially even physics has potential. But what we don't want to do is We don't want to constrain the model, because one of the other things that we learned from the OpenAI guys, what did we learn there? Is that we want to have an unconstrained, generalized model. The more unconstrained we are, the better the performance. All we have to do is add compute. So the second presentation I want to talk about is now, this is an engineering solution. Professor Ashwin from CMU talks about building a lens based on some actually basic optical engineering techniques, Lohmann lens, computational, prisms, and then local change of focus slopes, phase slopes, excuse me, that can then create an image that is taken in one shot and then sort of subdivided into different regions, and then those regions can have their own focus, and therefore you could have in rendering that image, you can focus on different parts of the image. So you could have 50 people and you can focus on 3 faces, and if you don't like that, you can focus on 5 faces. So this is the idea, and in my opinion, it's a very interesting idea because it's a technical solution, a hardware electrical engineering solution to a much bigger problem, which is 2 to 3D, right? The inverse graphics problem. Here, it's being solved with actual hardware and of course, computation. Ashwin talks about the ability to use his rendering technique for, let's say, 3D and virtual reality, applications. And there's only a small step from there to simulation. So we have this opportunity here to actually apply physics and real hardware and engineering to the same problem that Wu is trying to tackle. That's why I put these 2 presentations together. I think to summarize, this episode is about 2 to 3D. Jitendra Malik said in his presentation recently, this is about robotics. Convolutional neural nets have solved the self-drive problem. We need 2 to 3D translation to solve the robotics problem, and we can do that with computational techniques such as Wu's various attempts to use deep neural nets and foundation models to tackle the 2 to 3D translation. And then we also have Professor Ashwin's approach, pure optical engineering approach. I think we'll see some combination of those 2. And I think both of these presentations are steps in the right direction. We believe here on Launch Capital Partners, we agree with Jitendra Malik that solving the 2 to 3D problem is one of the biggest steps towards a more robust robotics pipeline, and that we could have actually pretty soon some very big advancements in robotics if we can solve this, because then we can apply a simulation at larger scale. With simulation, we can start launching robots and then use the data from those robots for even better foundation models and bootstrap the field. Thank you.